There are three terrestrial planets in our solar system: Mars, Venus, and the Earth. And they're all very different from each other. And that leads to the basic fundamental question: why are they so different? Why is Mars different from the Earth? And why is Earth different from Venus? And that is one of the questions that we really hope to probe into and come to some answers with the VERITAS mission.
Hi, I'm Stephanie Tumampos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. Now, according to Roman mythology, Veritas was the daughter of Saturn and the goddess of truth. However, in today's episode, we're not looking to the ringed planet for answers, but to our twin Earth instead, Venus. This episode of Down to Earth comes from the Instrumentation and Future Technologies Technical Committee of the Institute of Electrical and Electronics Engineers Geoscience and Remote Sensing Society. The Instrumentation and Future Technologies Technical Committee is a global, multidisciplinary network that fosters international cooperation to advance state-of-the-art remote sensing instrumentation and technologies. To learn more about this technical committee and how you can get involved, visit their website at grss-ieee.org/technical committees.
I work at NASA's Jet Propulsion Laboratory in Pasadena, California. I've been there for about 30 years. My original background was in mathematics, and I've switched over to doing planetary and Earth-based science using radar remote sensing for most of my career.
This is Dr. Scott Hensley. As you heard, he's a senior research scientist with NASA's Jet Propulsion Laboratory, or JPL, where he studies advanced radar techniques for geophysical applications. For over 2 decades, Scott has worked on most of the SAR systems developed at JPL.
When I first came to the lab about 30 years ago, the Magellan mission to Venus was just in the process of getting ready to collect data on Venus. So that was very exciting. It was my really first extended exposure to Venus.
Today, Scott is a project scientist for the NASA VERITAS mission. For him, working on VERITAS fulfills a dream he's had of returning to Venus since his Magellan days. It's also an exciting opportunity to learn more about how planets in our solar system have evolved. Knowledge Scott is hoping we'll be able to use to enhance our understanding of Earth. We hear all kinds of news about Mars missions. So why is this one focused on Venus?
Okay, so for Mars, we've heard a lot about Mars because basically the mantra for Mars exploration has been follow the water. And the reason we're following the water is because life as we know it requires water, and we know that Mars was wetter in the past. It had water on its surface from about 4 to 3.5 billion years ago before it dried out and became a desert world that it is today. Now, Venus is quite different than Mars, and we like to know, when does a planet become something like a Venus, or when does it become something like a planet like the Earth, or when is it something like Mars? So one of the things that makes Earth habitable, for instance, is plate tectonics. So this is the movement of plates, which allows basically material to be subducted back into the interior and recycles volatiles between the atmosphere and the interior. And that is what's sustained the habitability over long term on the Earth. Venus doesn't seem to have plate tectonics. So the question, why doesn't it have plate tectonics? Is it going to evolve plate tectonics? Did it have plate tectonics in the past? So these are some of the big questions we'd like to answer. When is a planet habitable or not? And how did they evolve that way?
Just for our listeners, what do we know about Venus so far?
Well, that will fill a textbook. So what we understand about Venus is, first of all, we know it's a volcanic world. We can see many evidences of volcanism in the past on Venus. We know that the surface is relatively young in a geologic sense, somewhere between 750 million to maybe even as young as 150 million years old. We know that there are formations on the surface of Venus called tessera. These are what we think are some of the oldest terrain on the surface and are like the continents on the Earth. So Earth and Venus are about the same size. They have about the same radius, and they have about the same mass. So if you think about it from an exoplanet perspective, they're basically identical to each other. Prior to the 1960s and the first visit to Venus, people thought our twin sister was really much more of a twin sister in the sense that they believed it was sort of like a tropical environment, potentially like the Amazon or the Congo, because it was cloud covered. It wasn't until, we started sending probes to Venus that we realized, oh, wait a minute. Venus is more of a fraternal twin than an identical twin to the Earth. But Venus is very, very different in that respect. Its atmosphere is much denser than the Earth. It's 90 atmospheres at the surface of Venus, which is equivalent to being about 100 meters underwater. It is very, very hot. It's 450 degrees Celsius, which is hotter than would melt lead. And its atmosphere is almost entirely composed of carbon dioxide. So in that contrast alone, you're asking yourself, why is Venus so different than the Earth?
Is it true that we learned about climate change through studying the atmosphere of Venus?
There is some element of that. Venus, as I said before, is almost a pure carbon dioxide atmosphere. It's about 96% carbon dioxide. And we know that that's one of the greenhouse gases. It's a gas that traps heat. And it's one of the things that maintains the very high temperatures on the surface of Venus. And that was one of the early modeling. When people realized how hot Venus was, people started looking about how can it be so hot. It's hotter than the surface of Mercury, even though it's farther away from the sun. And then people understood that that same mechanism could be operating on the Earth, obviously to a lesser extent because we do not have the same amount of carbon dioxide in our atmosphere. But as we've seen the carbon dioxide slowly creep up over the decades, we've also seen the temperatures creeping up as well. And it's that same modeling, that same dynamic of how the greenhouse gases heats the atmosphere is true at Venus and the Earth. And of course, we're hoping that we don't end up like Venus.
I hope not. You mentioned there's a lot of volcanic activity in Venus. How many volcanoes are we talking here?
I can't remember the exact number, but it's over 1,000 known volcanoes on the surface of Venus. So one of our big questions is we would like to know if Venus is still active today. So as I mentioned, we know the surface was maybe as young as 150 million years old. And we have examples from other missions that suggest that Venus may be active today or active in the more recent past as early as 2.5 million years ago. But we really would like to get that smoking gun evidence that Venus is still active today. And VERITAS has a whole host of ways that we get to try to do that. So let me just tell you about a few of them, things that we're looking at to look for activity on the surface. One is we are going to make radar imagery of the whole surface, and we're going to compare that to the imagery that we got from Magellan about 30 years ago. So this is going to provide a way to check to see if there have changes that have been going on over 30 years looking at the imagery. Another thing that we can do is, of course, we can look for changes in the imagery during the mission itself. We'll be there for our 4 cycles, about 2.5 years, and we'll look for changes in the radar imagery over that period of time. We're also going to be looking for changes using the Venus Emissivity mapper. We're going to be looking for hotspots. It's an infrared imager. It's sensitive to heat. We're going to be looking for recent flows on the surface that became active during the mission. We're also going to be looking for the outgassing of water from the interior, like we would get on volcanoes on Earth. They would outgas water vapor. Lastly, I'll talk about my favorite, which is related to a lot of my research on the Earth. And this is used as a technique called repeat pass radar interferometry. And what you do with that is you collect 2 passes of the radar. In this case, they'll be separated by 243 days, the length of a Venus day. And we can detect changes at the centimeter level on the surface using the radar. So if there's a volcano, for instance, that's inflating or deflating, we can look for centimetric level changes in that volcano during the time that we're making the observations. And this is a type of measurement that we do on Earth all the time with radar instruments orbiting our planet. And that's what, to me, is going to be one of the most exciting parts of the mission, is looking at that data and looking for these changes on the surface.
Coming up, we learn about all the work involved in preparing for a mission like VERITAS. Also, Scott shares some details on the innovations that are helping us advance remote sensing instrumentation and technology for the future.
Are you looking to make an impact in geoscience and remote sensing science? Then consider joining one of the Geoscience and Remote Sensing Society's technical committees. From environmental analysis to spaceborne imaging spectroscopy, Each technical committee advances innovative research and technology in a specific field of remote sensing. By joining, you'll connect with a community of passionate researchers and professionals who are fostering important international collaborations and steering global research agendas. You'll also gain access to the latest news and state-of-the-art research in the field. Expand your network, enhance your career, and make a difference. Join a GRSS technical committee today by visiting grss-ieee.org/technical committees.
Welcome back. Today, we've been speaking with Dr. Scott Hensley, project scientist for the NASA VERITAS mission. As Scott mentioned, this mission to Venus is going to help us understand how planets in our solar system have evolved. There's a lot to learn about Venus' surface, its volcanic activity, and its gravitational field. Bringing together collaborators from around the world, VERITAS is also an exciting opportunity to test new remote sensing technology and techniques. So, how is VERITAS different from the Magellan mission?
Well, the first missions to Venus were in the 1960s, the Mariner 2 probe to Venus. And Magellan was in the 1990s. But what it did is it made the highest resolution images of the surface of Venus, which allowed us to get our first global look in higher resolution of the surface. Now, missions to Venus, in order to get high resolution image, they need radars. Venus is cloud covered. And basically, you can't see the surface optically like you can on Mars or the Earth. And so in order to peer through those clouds, we use microwaves, which actually penetrate through the clouds and allow us to form images of the surface that way. Now, Magellan formed images with a resolution of about 100 to 300 meters of the surface, which was great at the time. It was a vast improvement over the previous data and helped us find a lot of information about the surface. The other thing Magellan did was measure the topography. So it measured the elevation of the surface. And it did that on about 20 kilometer spacings on the surface. VERITAS is also going to have a radar, but it's going to be what's called an interferometric radar, which means it has two antennas instead of one. And what that allows us to do is to make topographic maps as well as imagery at the same time. And the imagery that we're going to generate is going to have a resolution between 15 and 30 meters. So, a factor between 3 and 10 better than Magellan. And it's going to make topography maps with 250 meter resolutions and 5 meter vertical accuracy, 2 orders of magnitude better than what we had for Magellan. So it's going to provide much deeper and better insight into what's actually happening on the surface. In addition to the radar, we have an infrared spectrometer. And that is set to operate in windows that can peer through the clouds also. Now, we won't get quite the same spatial resolution as the radar, but what it will allow us to do is to find out information about the composition of the surface of Venus. And that was not present with the Magellan. So we have this combination of instruments, which is different than Magellan, and we have improved resolution. And it's that combination of information from the two that's going to allow us this big increase in knowledge about Venus.
Wow, the advancements in the technology since the Magellan mission are really significant.
You're absolutely right. This mission would not be possible in the time of Magellan. So a number of things have happened since then that allow this mission to happen now. So for instance, for the radar, with the radar, you don't get an image right away when you collect data. You actually have to do sophisticated signal processing to turn the collected data into an image. And unfortunately, the downlink race, the amount of data that we can send from Venus back to the Earth is limited. And so if we want to get global coverage, the way we made that possible with VERITAS is we actually used the improvements in computer processing technology to actually do processing of the radar data on board and downlink the images directly back to Earth instead of the original raw data. And that allows about 1,000-fold improvement in the data that we can send from Venus to the Earth. So that's just one example of the technology changes from the time of Magellan to now that make this mission possible.
That's quite amazing. I mean, how much technology has really jumped. I just wanted to know how much preparation goes into a mission like this.
Well, a lot. So we've been working on this versions of this for about 10 years. This is the last iteration. And in this iteration, it was about 3 years of activities involved in preparing the mission. So, we have to do all sorts of studies on what's the best way to get to Venus, what's the right orbits that we have at Venus, what's the right instrumentation that we want to have to answer the science questions that we are trying to get at. We have to have models to predict the performance, how well we're going to do. We have to figure out what the exact science questions we're going to ask and how well we're going to be able to answer them. And then we have to go through a rigorous review process by NASA that goes in 2 stages before being selected. So it's a long and an arduous process to go from the basic idea, we want to go to Venus and have a mission to look at the surface, to here's what we're actually going to do and how we're going to realize that to make it all happen.
It seems like the mission is really huge. Can you give us some specifics about it? Say, how many people are involved? When will the VERITAS mission be launched, and how long will the mission last?
Okay, so there will be hundreds of people involved from both at NASA, at the Jet Propulsion Laboratory, and other NASA centers. We also have the spacecraft provider, which is Lockheed Martin. And then we have foreign contributions that play an integral role in the missions. For instance, the German Space Agency is providing the infrared spectrometer I talked about. That's going to look at the surface composition. There's also another team at the German Space Agency who is an expert on radar interferometry like myself. They're going to be helping with the processing algorithms and some of the system modeling. We also have the Italians who is contributing a portion of the radar for the radar instrument. We have the French who are contributing part of the communication system to go between the spacecraft and Earth. So we have all these different components, and each one of these have various teams working on this. So many hundreds of people will be involved over the lifetime of the mission. Our duration of our mission is what's called 4 cycles. And what a cycle is it's about 1 Venus day. Now, one interesting thing about Venus is a Venus day is much longer than an Earth day. So it's about 230 days or so. Since Venus rotates very slowly, we're going to basically collect data over 4 Venus days as the spacecraft will orbit while the planet rotates very slowly beneath it. And that's part of our whole mission plan.
So I'm really interested in this and excited. Before we move further, I would just like to ask, what is the significance of the VERITAS name? Why did we call it VERITAS?
Well, VERITAS stands for Venus Emissivity, Radio Science, InSAR, Topography, and Spectroscopy, which are the various aspects of our mission that the instruments and the science that we're planning to do. And of course, that spells veritas, or truth, in Latin. And so we're looking to find the truth for Venus. And so we just thought it was sort of a nice acronym that had a really simple core message for the mission.
So if you had to share with the average person why VERITAS is so important, what would you say to them?
So it's intrinsic to human beings to want to understand nature. And this is just part of our intrinsic interest and curiosity for understanding our environment, the world, and the solar system beyond us. In terms of the specific benefits that may also be incurred by this mission, and if we look to the broader science that VERITAS might answer beyond understanding Venus itself, we hope to get a better understanding of how terrestrial planets in general form throughout the entire galaxy. So we really want to get a more consistent and more detailed model of how terrestrial planets come to be in their state. And VERITAS will definitely contribute to that broader knowledge. It also is going to help us in comparative planetology in terms of understanding how and why the Earth, Mars, and Venus are different from each other. It turns out the data sets we have for Mars and for the Earth have much higher resolution than we do for Venus. By gathering these higher resolution products that we're gathering there, we're going to be able to do a much better job of comparative planetology. So we're going to improve our relative understanding of the various terrestrial planets in our own solar system. So this mission is going to help not only in the specific Venus science it's designed to investigate, but also in understanding broader aspects of our solar system and exoplanets beyond our own solar system. I hope that when we start collecting data that everybody will be really excited to be seeing our first images from VERITAS and will be excited to join us in our exploration of Venus as we get the data, and we invite everybody to really come on board and explore Venus with us.
Well, that's all for this episode of Down to Earth. To learn more about the VERITAS mission and Dr. Scott Hensley's work, search for VERITAS on the nasa.gov website. Don't forget to follow us on Spotify and Apple Podcasts. And send some love to our sponsors at IEEE_GRSS on Twitter and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Killam Media. And a special thanks to Fabio Pacifici and Keely Roth for their support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.